Hey everyone, welcome back to my math channel. Today we're covering the chain rule, which is very important in calculus and allows you to find the derivative of composite functions. A composite function is just a function within a function. So for example, if you have something like f of x, that's one function, or g of x, that's one function, but f of g of x is a function within a function, or a composite function. So how would you find the derivative of those without using identities to modify some of them? And for that, there's a rule, which is called the chain rule. It's called the chain rule because it's a chain of functions within each other. And the proof, I'll go through this on the screen because I did this a little bit before. So like normal, I always start with a limit definition, which is why I have this line f of g of x plus h minus f of g of x all over h. And then what I do is I multiply and divide, I multiply and divide by g of x plus h minus g of x. So that means both the numerator and denominator are multiplied by the same expression so that it's still equivalent. And the g of x plus h minus g of x on the numerator gets divided by h, so that this looks like a standard limit definition, something like what's over here. And so that will just become g prime of x. But what about this? This entire section doesn't look like something we have that's kind of familiar. Well, in a way, I guess it does. On the denominator, although it only shows h, that's because it's actually x plus h minus x. And since the x's cancel out, you only get h. So using that logic, you could group x plus h and x separately. And that's what kind of shows in this expression. We have g of x plus h minus g of x on the denominator and f of g of x plus h minus f of g of x on the numerator. So in this case, this limit would become f of x because you have x plus h instead of some output of x. But if you have some output of x, like g of x, instead of x, you would get g of x plus h minus g of x. And so oh, this should be f prime. And so then your derivative would be f prime of g of x. So that kind of leads me to this derivative of the chain, of this composite function, which is f prime of g of x times g prime of x, with f prime being the function on the outside and g prime being the function on the inside. And although there are only two functions, you can do the chain rule with multiple functions within each other. And this kind of seems a little bit like the movie Inception because you have a lot of dreams within dreams within dreams. And it's like a cascade, kind of. So the first question I'll give is a chain, one with functions that seem kind of simple. Sine x to the power of 4. Sorry, or I'll just say sine, yeah. So if y is equal to sine x to the power of 4, which I wrote like sine 4x. And for positive integers, this notation works, but for negative integers, it doesn't work as much. And we'll see why a little later. So what I would do is, I would normally find what the innermost function is. So this can be written as sine x all to the power of 4, which for the purpose of this problem helps. So you'd want to replace the inner function with some variable, u. I'll call it u. So that means u is equal to sine x. That also means y is equal to u to the power of 4 because of how composite functions work. So if we want to find the derivative of y with respect to x, that means we need to find the derivative of y with respect to u and then multiplied by the derivative of u with respect to x. So algebraically, it looks like these cancel out, but from a calculus standpoint, you're finding two separate derivatives and then multiplying them together. So in this case, we have we're taking the derivative of u to the power of 4 with respect to u, and then we're multiplying it by the derivative of sine x. And then that's the derivative, the final derivative we actually have. So that means, using a power rule, we have 4 times u cubed multiplied by cosine x. But we didn't start with the function u in our original question, so that means we can't finish with it either. So whatever value we had for u over here, we have to substitute it back into our original function. So that means u cubed just becomes sine x all cubed. So that means this would be our final derivative. So you get the idea, I'm hoping. So let's try another question. And this time it'll still only be with an 1 in a function and 1 out of function, although I'll progress to multiple by the end of this video. Try e to the power of x squared plus 1. Why don't you try and pause the video and see if you can get it. Ready? Okay, so our inner function is whatever's in the inside of everything. So that means if we have an exponent on the outside, if we have an exponential function, our exponent should be the inner function. And so that means it's x squared plus 1. So we'll say u is equal to x squared plus 1. And that means y is equal to e to the power of u. So that means the derivative of y with respect to x is equal to the derivative of with respect to u multiplied by the derivative of u with respect to x. And I can just say dy over du times du over dx. That is much shorter to say, but I guess I don't know how well you understand it at this stage without any feedback, so I'm just playing it safe. So now we have dy over du, and so that means we differentiate e to the power of u with respect to u, because that's what's on the denominator here. And then we multiply that by the derivative of x squared plus 1 with respect to x. As we found out in a previous video, e to the power of x is the derivative of itself. So that means this derivative just becomes e to the power of u. And then the derivative of x squared plus 1 is 2x plus 0, because the derivative of any constant is 0. So this just becomes 2x. And now, like before, we have to get the value for u back into this original question, into this final solution, because we didn't have u in the original question. And since u is x squared plus 1, it only makes sense that we write x squared plus 1 over here. So that's the final derivative for this question. It's kind of a tongue twister of a word, to be honest. And now this last question, there will be a function within a function within a function. And you can do this with like 10 functions, 100, although it would just be time consuming. It would be more time consuming, but the main premise of using the chain rules stays the same. So we have let's use one of the trig functions from the previous video about the quotient rule. Let's say we have tangent of e to the power of 3 cosine x. So Why don't you pause the video and see what would happen? First, I would suggest that you find out what the innermost function is and work your way backwards. Pause the video and try it for yourself. Ready? So the innermost function is when you start from outside and get all the way to something with x. So in this case, you start from outside and you get all the way to 3 cosine x. So that means we'll say u is 3 cosine x. And that means that this function is equal to e to the power of u. But then even that's not the outermost function, so that's not equal to y. So we'll put that equal to some other variable v. And so that means we get tangent v. And since that's on the outside, we'll set that equal to y. So now when we take our derivative of y with respect to x, which is dy over dx, we have to do dy over dv multiplied by dv over du multiplied by du over dx. And algebraically, this looks like it cancels out really nicely. In reality, it's just 3 separate derivatives. So now let's actually get to the derivative part. And now we have our equation set up, so this is now slightly easier. So we have the derivative of tan v, or tangent v, multiplied by the derivative of e to the power of u, multiplied by the derivative of 3 cosine x. And all of that is dy over dx. So now what we need to do is, what's the derivative of tangent? It's secant squared. So that means we have secant squared of v. And then we multiply that by the derivative of e to the u, which is itself. So we have e to the power of u. And the derivative of 3 cosine x is negative 3 sine x. So now we have the variables v and u, so we need to substitute back. And since v is equal to e to the power of u, we'll do secant squared of e to the power of u multiplied by e to the power of u multiplied by negative 3 sine x. And I'll bring the negative 3 to the left because that's like standard writing convention in math. And now we still have u, which we need to get rid of. So now that means e to the power of u becomes, well, secant squared of e to the power of cosine x. Sorry, my bad, 3 cosine x multiplied by e to the power of 3 cosine x times sine x. And that's our final derivative. Anyways, thank you so much for watching this video. I hope you learned something out of it. And before I part, I guess like chain rule is just finding the derivative of functions within functions. And you do that by finding the derivative of each like basic function separately with respect to some variable, and then just substituting the variables back. I hope that helped, and stay tuned for the next video. And until then, just keep practicing. Also, please drop any feedback in the comments. And one more thing, like I promise I'll not be too long. I think the audio quality in some of my videos has been off, and I'm hoping that won't happen soon because it was fine on my laptop. So if you would like me to type in a description of what happens in the comments somewhere, please let me know. Anyways, thank you.